Hello, my name is Jonah Rizabalaga, and I am a PhD student at the Technical University of Munich. Today, I'll be presenting SCTOMP, a specially constrained time-optimal motion planner. This is a joint project with my supervisor, Professor Marcus Rill. Motion planning addresses the problem of finding a trajectory that drives a system from a starting state to a goal state without violating spatial and system constraints. Traditionally, this problem has been solved by decoupling it into two separate stages: path planning and path tracking or path following. Firstly, in the path planning stage, a collision-free geometric reference is found according to task-related high-level instructions. Secondly, the path tracking path following stage finds a dynamically feasible trajectory to track this predefined geometric reference. When aiming for time optimality, most of the literature focuses on the second stage, either with time optimal path tracking or time optimal path following. However, the optimality of both methods is highly biased or even upper bounded by the geometric reference predetermined by the path planning stage. In other words, decoupling the motion planning problem into two separate subproblems compromises the methodology's overall optimality. Aiming to overcome this limitation, a few attempts have been made to formulate a unified and coupled framework. Despite achieving a greater performance than the decoupled architecture, none of these attempts can guarantee the computed trajectories to be globally optimal, either because of their non-deterministic or learning-based nature. This situation leads us to the research question that we are trying to answer in this work. Given any constrained environment and any dynamic system, is it possible to formulate a motion planning method that guarantees time optimality while being compliant with spatial bounds and system constraints? Trying to answer this question, in this work we present SCTOMP, a three-stage time-optimal motion planning method that solely requires an occupancy map of the environment, as well as the initial and goal locations. First, it finds collision-free navigation corridors. Second, it computes an obstacle-free Pythagorean Hodograph parametric spline associated to each corridor. And third, it solves a spatially reformulated minimum time optimization problem at each of the corridors. From the obtained trajectories, the one with the lowest navigation time is selected. In contrast to the aforementioned decoupled approaches, the parametric paths obtained in the second stage are not a geometric reference, but an extension of the free space associated with the respective corridor, and consequently have no effect on the optimality of the time minimizing problem in the third stage. To evaluate SCTOMP, we have divided the experimental analysis into two parts. In the first experiment, we demonstrate that the solution's time optimality is agnostic to the PH spline computed in the second stage by comparing the navigation times obtained for 4 different splines in a racetrack for miniature cars. All 4 solutions result in the same trajectories as stated by state of the art, exhibiting equivalent lap times and thereby confirming that the solution is independent of the underlying PH spline. In the second experiment, we study SCTOMP's applicability to spatial systems within more challenging scenarios by focusing on a benchmark that entails navigating in two cluttered environments, a forest and an office. More specifically, we compare SCTOMP's performance against two state-of-the-art approaches, a hierarchical sampling-based method and a reinforcement learning-based method. The results indicate that for the majority of the test cases, SCTOMP is able to compute trajectories with the minimum navigation time. On the one hand, the excessively hierarchical procedure of the sampling-based algorithm jeopardizes its time optimality. On the other hand, aiming to account for tracking disturbances, the RL method learns to prioritize safety over time optimality by avoiding to fly too close to the obstacles and thus rendering the obtained trajectories suboptimal. In contrast, SCTOMP fully exploits the free space within a given corridor, resulting in trajectories that tangentially touch its borders, as depicted by the purple lines in the plots. This is everything from my side. For further details, check out the paper. Thank you very much for your attention.